Hello, my name is Jakin Ramirez, and I'll be discussing virtual process modeling for metallic additive manufacturing based on direct energy deposition. So, what does that mean? Well, the entire goal of this is to reduce internal stresses for a particular part. What it means specifically by that is this. In additive manufacturing, you'd normally associate that with a 3D printer as a machine that creates parts by adding small amounts of material, such as plastic, in layers until a complete part is made. We're taking that concept and applying it to metal. So this is called MAM, or metal additive manufacturing. The way this works is that you take an amount of powder that is metal or wire that is powder into a certain region and melt it. And this results in metal parts that are more inclined for heavier loads. Now, the drawback to this is that plastic has a give to it when it's printing. Metal does not. This is because as it expands and contracts, when it heats up, it pushes on the neighboring particles of metal. And this results in failure. So, how do we get around this? To minimize the internal residual stresses that cause these failures, we'll be using ANSYS, AMDED process, which is an additive manufacturing simulator. Now, the way that we approach this is that we will go to SolidWorks, make a model, pop it into a geometry ANSYS file, and make a mesh from it. So it's a way of cutting up the geometry into small pieces for ANSYS to go in and simulate at a single moment in time. Now, the difficult part is that you have to specify where the nose or the extruder of your machine will go. And so I decided to make an in-house G-code to make these extrusions in a very particular way so that I have complete control of how it does this. They are visualized here. Now, not every line gets printed out, only certain ones do, and that is specified through G0 and G01. After I get the code for one layer, I simply repeat them so that each layer is repeated the exact same way. Now, after all of that is said and done, we can finally do a study, which will be specifically for a transient thermal scenario, and then from there, we do a steady state structural study. And from there, we have these results. Now, the idea behind the first column is clustering. Basically what's happening here is that it's taking the G-code that was made and giving it an element to follow with it. And that's the element that is being analyzed. Then the thermal study is executed. This allows it to find what's heating up at what time using a dead or alive mechanism. And then a stress analysis is conducted. I believe that von Mises stress is used for distortion energy theory that's used for finding a safety factor. And this will help us find where the stresses are in a given part that we have. Now, there is also this one where we explore the minimum and maximum principal stresses, which is just a simple word of saying tension and compression, figuring out where it's pulling in and where it's pushing out. Now, the idea behind this is to find certain printout patterns that have less internal residual stresses as a result from the printing pattern. So as you can see here, we're looking at different printing patterns that would allow less internal stress. And this would usually be done iteratively through certain scenarios. that we would analyze separately. Up over here to the right is a parameter study, where we would be experimenting with the melting temperature or extrusion rate to help reduce internal residual stresses.